I designed this as a kind of leisurely talk, so please, so the idea is that you interrupt me at any moment and we can discuss things. And I really try to explain certain things. So yeah, I hope this this will work out. So,
Albert, leisurely for you and high octane for everybody else, of course.
I hope that's not that will be proved wrong, Sergey. I will do my best. Yeah, and also okay, maybe something about the motivation. Of course, I'm looking at, so part of the motivating things are certain counterexamples, but I think the motivation of all this work is not just breaking new ground, but also re-understanding or understanding better the traditional material, right? So the things that were in Boulos and Smorinsky's books to re-understand this. Okay, so yeah, what's going on here really started when I had to referee a paper, and this was all about the uniqueness of Gödel sentences. And then I wondered whether this uniqueness of Gödel sentences would also hold when the second Löb condition, provable implies provably provable, was lacking. And so I thought, in fact, I thought, of course, that should fail. But then I had a store of examples where we had the second incompleteness theorem, but not the second Löb condition, provable implies provably provable. And then to my amazement, it turned out that in these examples, we still had the Jongh-Sambin-Bernardi Theorem. And so that really led me to rethink what was going on here, and that led really to the research that you're seeing here. But before we go into this, I want first to say a little bit about the kind of generalization of Gödel's theorem that plays a role in the background. So that shows that for a wide class of theories where we don't have the second Löb condition, we still have the second incompleteness theorem, and that will be, as it were, the starting point of looking at the more general provability logic. Okay, so what does Verfermann's version of the second incompleteness theorem look like? And yeah, for me, in some sense, this is the classical formulation of the thing. So as the basis in the background, Verfermann's idea is to fix a predicate proof, and so it has a second order plug-in variable, and then a first order variable x and y, and it means x is a proof of y from axioms in x, where so the x is a unary predicate symbol, and then we write provable alpha of y for exist x proof alpha x y, where alpha is the result of replacing the second order variable by a formula from your language, right? So that's the thing that Verfermann's supposed to be fixed, and I think this move, so which probably was a usual move, but Verfermann made it explicit in his 1960 paper. And then you get the following statement, right? Consider any consistent RE theory T and an interpretation K of EA plus B sigma 1 in T, and let sigma be a sigma 1 formula, and suppose that sigma K semi-numerates the axioms of T in T. And so semi-numeration is simply that if something is an axiom, then the theory proves sigma of the Gödel number of A, right? It's not an if and only if, it's the weak form. If true, then provable, but you don't need the converse for the second incompleteness theorem. And then the statement says that T does not prove the consistency of K with respect to sigma, right? And so here we are quite precise. We don't write T, but sigma to remind us of the axiom set. Now, yeah, so of course, Fefferman formulated it for PA, but in fact, if you analyze his proof, it works without any problems as for EA plus B sigma 1, but the B sigma 1 is essential, because otherwise Fefferman's proof doesn't work. And the reason it doesn't work is that the second Löb condition may fail when we omit B sigma 1. But it turns out that by a modification of the proof, you still can get the Fefferman's result. So we can leave out B sigma 1, but you need a slightly different proof. And in fact, very roughly, I will give that proof. So here you have two important examples. So, so you can give a sigma 1 numeration, sigma of the axioms of elementary arithmetic, which is I delta 0 plus exponentiation in elementary arithmetic. And here it's really enumeration, right? It's if and only if, it's not more. And of that numeration, EA can prove that the number of axioms in the set given by sigma is finite, point 1. EA cannot prove that box con is equivalent with box falsity. And yeah, to my surprise, EA proves that the Gödel sentence is equivalent to con in con. And so, yeah, so that's, so regrettably, don't ask me to give the example. I really have not prepared it, and it uses Fefferman's adaptation of Fefferman's arithmetical completeness theorem. So it's really, of course, a tricky example. You really have to construct this with great care. Yeah, so the Löb conditions fail for EA in combination with such a sigma 1 axiomatization. However, G2 for sigma 1 semi-numerations does hold completely generally. Okay, so here is also a celebrated example due to Fefferman, which is important to keep in mind. So you have consider the standard predicate representing PA's axioms. So then we define P of X of Y as the axioms that are smaller than X. And then P star of Y is P of Y and, sorry, pi of Y, I should say, and con pi of Y. And so, so now note that this pi star is pi 0, 1. And it so okay, this is all Fefferman's insights, right? Pi star enumerates the axioms of PA and PA. On the other hand, we do have the consistency, right? So that's and so what you see here is that the sigma 1 in the statement of Fefferman's theorem is really needed. You cannot get around this so simply. But so if you want, so what's happening here, right? What's happening in this example? And so what the thing that is going on is, yes, PA can enumerate the axioms of PA with respect to P star. So that's no problem. But the to enumerate the first K axioms, you always need more than the first K axioms, right? So the axioms that you need for enumerating the axioms are always more than the axioms you enumerate, right? But since we have infinitely many axioms, of course, you can always use more axioms to enumerate less axioms, right? So that's what's going on in the example. And so, yeah, my trivial insight is really that, in fact, that is all that goes wrong in Fefferman's example, right? So if we block if we block this phenomenon that the axioms you use to enumerate the axioms outrun the axioms you enumerate, if you block that, then you're fine. And so that leads to the notion of uniform semi-numeration. So consider your consistent theory, let X be your set of Gödel numbers of axioms. And now the important thing is there's no constraint at all on the complexity of X. It can be sigma 0, 100. It can be sigma 1, 15. It can be completely outside of any thing that we can do to classify complexity. It is not relevant. So now suppose that UK is the theory that is axiomized by the first K axioms. And then finally suppose that we have an interpretation of some appropriate weak arithmetic in U. And then I say that a U formula Xi uniformly semi-numerates X if for every n you can find an m larger than n, such that um proves Xi I for each I in Xm, right? So for every n you can find some larger number such that you have the theory Xm that semi-numerates its own X, such that Xm gives you the theory that semi-numerates its own axioms with respect to Xi, right? So that's the whole thing, right? So if you go to the limit, that you always have these resting points where you have subseries where that semi-numerate their own axioms using Xi. Is that clear? So this is really precisely the statement that says we do not have the kind of Pfefferman counterexample cannot work. Is everybody there? Sergey?
Yes.
I'm just muted, so that's why I try to say something, and then I realize I have to press the space bar. Yes, everything is fine.
Good. Okay,
Don't
and now
the first K axioms rather than axioms with Gödel numbers.
Yeah, okay. I probably it's better to say with Gödel number smaller equal than K, right? Because that's what piano or what your arithmetical theory understands most easily. Yeah, so let's make them a Gödel number smaller equal than K, because maybe the enumeration of the axioms could be something crazy. Yeah, you're right, Lev, so I should have said it. Okay, and then we have, of course, suppose U is consistent, and so it could be of any complexity, as I said. Suppose Xi uniformly semi-numerates the axioms, then it doesn't prove, U doesn't prove the consistency, right? So I use the square brackets here to remind you that so the consistency statement in some sense lives in N, inside your internal model of the natural numbers, but no, Xi of course could employ the full language, right? It's not an internally defined arithmetical predicate. So now of course the proof of this incompleteness theorem becomes completely trivial. So suppose U would prove its own consistency, then for some K we would have that UK derives Bn. I will say in a moment what Bn is, plus the consistency statement, and Xi enumerates the axioms of xk, and the axioms xk of semi-numerates the axioms xk in UK. So B is simply the single sentence that axiomatizes my basic arithmetic, right? So it's essential here that we take a finitely axiomatizable one to do that.
Beta should be B, yes?
B, yes, yes. B.
It's beta on my screen.
Yeah, well, no, so the big B is the sentence really that says
Oh, yeah.
S12, right?
Yeah.
And the beta is the formula that axiomatizes the finite set xk in a standard way. So now it has since
Big B is bus.
Yeah, big B stands for bus or for basic. Yeah, precisely. Okay, and now, of course, it's trivial to see that if we can prove something from beta, we can also prove it from xi, right? Because the theory knows of the standardly many standard axioms in xk that they're in xi, that's the semi-numerability. And so if we have a proof from these things as given by beta, the theory can see that we ipso facto have a proof from the axioms given by xi. So from the xi consistency, we get the beta consistency. So UK proves B plus the beta consistency of UK in N. But then now we have reduced everything to finite series, right? UK is a finite series, beta is a trivial predicate defining the axioms of the finite theorem, and so we are back in well-known territory, and we can simply apply the Gödel's second incompleteness theorem in a well-known version here, or maybe in the Pfefferman version, but you need even much less. And that's it, right? So we have a contradiction. So that's the trivial argument for my version. So yeah, of course.
Let me check. So if you have a sigma 1 numeration of PA in PA, for example, standard one, it does not necessarily is uniform semi-numeration.
It's going to be necessarily uniform, because whatever is truly in will be in already when we have let's say enough axioms to give you EA, right?
Because we have finite fragment in which
sigma
completeness
already
is called.
Yeah, precisely. Yeah, so that's automatically, so all sigma.
Okay, good.
Yeah. Of course, we can make all kinds of crazy examples, but this kind of example, of course, is automatically in the fold. Okay. Now the nice thing is so I proved this, but then as an afterthought, I saw, well, of course, the uniformity can be easily lifted to finite extensions, right? So if we have uniform semi-numerability for theory, we trivially have it also for a finite extension, and hence by the well-known trick, we can extract Löb's principle from the second incompleteness theorem. So in fact, if you have a uniform semi-numeration, then you also get the Löb's rule, right? The theory U will be closed under Löb's rule. Okay, and so that shows that there's at least a kind of wide class of salient theories that will not necessarily have the second Löb condition. Provable implies provably provable, but we still have closure under Löb's rule. And so it turns out that if you have this closure under Löb's rule is sufficient for the Jongh-Sambin-Bernardi, right? The uniqueness of fixed points. So as soon as you have this, then we also have things like uniqueness of fixed points, etc. Okay, good. Okay, so now, okay, this is a kind of natural point. So are there questions about this until now? So in fact, this really only functions as a kind of supporting talk for the rest of the talk, right? Which is about modal logic. And but at least I want to motivate that yeah, this closure on the Löb's rule is a kind of widely present phenomenon that is not really that doesn't really need closure under the second Löb condition.
Yes. So so what you have here is that for this uniform semi-numerations, you will have the logic of such a proof probability predicate will be something like at least k plus closure under plus
okay,
something plus closure under this rule. But,
yeah,
k
right.
itself is closed under this rule, therefore we don't get anything interesting for k itself.
Yeah, that's precisely, that's very,
Yes.
very good, Lev. That's precisely the point here. And so, in fact, people have, so people have studied these logics, and they I think there's an example of by Kurahashi of a sigma 2 axiomatization of PA where you precisely get k. And so indeed, if we use the standard language, we are nothing interesting needs to happen. But my claim is that a good provability logic should have fixed points. And so that's of course the plan to add fixed points. Okay, so yeah, now we're at this point. So now the whole idea is to develop provability logic for arithmetical interpretations of provability that satisfy Löb's rule. And so the idea is simply k plus Löb's rule plus fixed points. And so together with Tadeusz Litak, I started working on this, and so we worked hard to develop a series of logic of provability logics or überhaupt of modal logics, extensions of k with fixed points. But we did this for the kind of standard language. So we simply we had a fixed point operator d gamma p that did these things, but so I couldn't help feeling that this is not, in some sense, this way of doing it is not, it doesn't really reflect what's going on, because if you think about, if you work this out, there's a lot of things about binding, and in fact, the whole thing is not about binding, but more about cyclic phenomena. And so, so parallel to my work together with Tadeusz, I started thinking about cyclic syntax. And so there's really two prima facie ways of doing this. So using fixed point operator and using cyclic syntax. And I claim, and I think I know the proof, the two ways are equivalent. But on the other hand, of course, the relevant notion of sameness has not been developed. So this is a kind of nice example where you know the proof, but you don't know the theorem, right? So, so the provability logic on cyclic syntax is the same as the provability logic with a fixed point operator in the standard language. Only, so what is the notion of sameness that shows this? So this still has to be worked out, and I simply have to do that. So there's a third way, I think, to get a handle on this, and that's using systems of equations. And it's only a few days ago that suddenly I think I saw the light about this. So I think so if you add systems of equations and simply add constants for the fixed points, of course you do get not a logic but a series, right? Because the point, of course, is that with the fixed point operator there are the free variables under the fixed point operator, and here we only have a series. And so only now I understood that you really have to think about two kinds of morphisms, right? So the kind of morphisms, interpretations between series that are adequate for logics, and interpretations between series adequate for series. And I claim that probably both, so I haven't worked it out, but so my claim is that if we use the interpretations that are adequate for series, then all these three approaches are the same, of course. But if we use the method that is adequate for logics, of course, only the first two are equivalent and the third is not, right? Because it's not, in fact, not a logic, right? So I think that's probably what is the case here. But yeah. Okay, so the theory was the traditional syntax I call the Henkin calculus, but so I went to calling the other thing cyclic Henkin logic to distinguish it. Okay, so so this whole idea, of course, to use a richer kind of syntax. I think there's probably thousands of examples that I'm not aware of, but so Barwise and Etchemendy's use of non-well-founded set theory to model circular propositions, that's, I think, one important example. And what I'm doing here is really more or less directly inspired by Barwise and Etchemendy. We have Peirce's existential diagrams, also one of my favorites. Hans Kamp's discourse representations. So people also use type lambda calculus as a kind of proto-syntax. There's the set notation for clauses and undoubtedly many more. But so what we are going to look at is really inspired by Barwise and Etchemendy. And so in fact, I could develop everything in this non-well-founded set theory, but I think that would be a bit heavy material for the case where I'm just looking at finite things. Okay, so what are the advantages of syntax on graphs? Okay, it affords us a kind of very visual way of understanding things. For example, so I always understood the multiple fixed point lemma in Smorinsky's book by following the steps by hand, and but that's here it's immediate, and also the asymmetries that are in the usual proof are lacking in the graph theoretical proof. Okay, but moreover, graph theoretical ideas become available, so I can use notions like bisimulation minimality, unraveling, co-induction, co-recursion, etc. And so it turns out that the first half of the Jongh-Sambin theory on the existence of explicit fixed point, that turns out, if you look at it in a graph theoretical way, as purely syntactical, right? So the strange thing is that the explicit fixed points construction really has two completely different stages. One stage is purely syntactical, and the second stage is really theory dependent. But that you can only see if you have the kind of this kind of framework available. Okay, so as an appetizer, here is the proof of the. I haven't told you yet what graphs are, etc., but here's the proof of the multiple fixed point theorem, right? So we have equations P if and only if phi and Q if and only if psi. and we want to solve those. So yeah, can you see my, so here we have,
we can see it.
yeah, so you can see the little hand, right? So
Mhm.
here you see the formula phi, and it has variables p and q, which I have exhibited as exit gates. Here you have psi, and here you have p and q that I have exhibited as exit gates. So how do we solve the equations? Right, simply take phi and psi and identify the exit gate p with the root of phi for both cases, and identify the exit gate labeled q with the root of psi in both cases. And then you get this graph, and that graph gives us the solution, right? The solution of the one is for p is when we take this root of the graph, and the solution for psi is when we take this root, right? And so you have a completely trivial proof of the fixed point theory. Okay, we will see, of course, that there is a little bit more to say, because so Löb in a previous talk expressed the fear that the thing would be inconsistent. And of course, there should be some guardedness condition for this solution, right? We shouldn't be allowed to form the liar paradox. And so there's, yeah, but we will see. I cannot say. So we will see how the guardedness solution works. Okay, so now what is a graph? Well, a graph is given by a finite set of nodes. It has a root. That is, we are looking at the labeled graph, and we have a successor function for every node or vertex. So we send the vertices to finite sequences of vertices, and including the empty sequence. And so the labels that I have, I suppose that they come equipped with an arity function that tells us what the arity of what the numerosity of the outgoing arrows will be. And so what we ask is that the length of the successor is the arity of the label, right? So if we have the label as a conjunction, then the successor will be a pair of nodes, and so and if it is a negation, the successor will be a single node. Yeah, and so I think it's reasonable to demand connectedness, namely that every node can be reached from the root via a pass. And okay, it turns out that there are really two definitions of pass, namely one where you do not add whether you take left or right turns or whatever, right? You have no direction information. And there's also a notion of pass that incorporates the direction, right? So I'm first going to the left and then to the right, and then I take the second road from the left, etc. And if you try unraveling, you need this notion of pass that incorporates the directions. Now here's of course
a question. So is it important to think about these graphs in these functional terms, where you have this? I mean, you have this labeling function, and this in particular this S function in finite sequences, or is it just your way of presenting the more or less what we all understand as labeled graph?
A really great question, Löb. So okay, the answer is no, it's not needed, but you have to do something, right? Because so for conjunction, for example, we do not need an order on the successors, but for implication, we do need one, right? So you should. So what also would work is, for example, so you have a set of nodes and arrows. You have a source and a target functions, and then you have and the arrows are either labeled plus or minus. and then you have a number of constraints on the right. So if the node is labeled conjunction, then I can ask that all nodes are labeled plus or whatever, right? So yeah, you can do it in a different way, but I think the nice thing here is, so this is the format that is used in co-induction, right? So this is the co-inductive. So there's a lot of theory about this, right? This is the co-inductive representation of a graph. And so, and I think that really the true way of thinking about what's happening here is co-inductive. So I choose this one because it's in line with a lot of theory formation, but it's not needed. And for example, so what I like is, for example, so in the Peirce diagrams, in the existential diagrams, so Peirce doesn't want an order for conjunction, right? So you can build in. So you could say that the conjunction is simply something with a set of successors, and then you don't need falsity because that's conjunction with the empty set of successors, etc. Right? So you can do all kinds of interesting things also in the other format. And so so this is really possible, but there's at least one argument to have this framework. But
sorry, why is this, maybe you said that I missed it, why is the set of all sequences of element in n, what is a natural number is denoted again as v star, or the design is meant to be v?
Sorry?
So you say that
elements
f
in v.
Okay. Sorry. This is
okay. So this n is
I
a typo.
see. No, you're right, completely right. So this is because I switched from calling these things nodes to calling them vertices.
Oh, I see.
Yeah.
I thought these were natural numbers or something.
Yeah,
Okay.
no, it's really
by the way, Albert, this typo is in the paper that you sent us as well. So you check it out there as well. So
yeah, that's also because of the copy and paste. Okay, now there's a very important notion of equality of graphs. So the intention is, of course, to think about graphs modulo bisimulation, right? So that's the intended notion of sameness. And so, but for all kinds of purposes, it's good to really also have the concrete representations at hand. So I do think in the first place of them as modulo bisimulation. I'm sorry, modulo isomorphism, right? So this really means that what we choose as the underlying vertices is immaterial, right? So the things that have real identities are the labels. So yeah, so what is a bisimulation? Between two graphs, it's a relation R between the nodes. So I demand that it relates the roots. So that really immediately causes it to be total and surjective. And I demand that if it relates A and A prime, that then the labels are the same, and then that all the successors are also are related, right? So that's it. And yes, and so I use this notation here for bisimilarity. Okay, and so
what would be a simulation in this case, one way?
Yeah, so simulation is the one-way thing, right? Where we just asked, well, yeah, I think here we're in, as I formulated it, because of our specific framework, the bisimulation would
you don't have simulations.
I cannot really distinguish it well but in the general case, of course, the simulation is you really just have the forward clause and not the backwards clause. But here, because I have this strict regimen for what the successors are, by a simulation almost doesn't exist, I guess, right? I wouldn't know what it is in this specific case, but in the general case where we have a graph more in your sense, Löb, it's simulation is completely clear, right? You just have the zig clauses, but not the zag clauses, right? Not back, not forward, but backward. But here you see that here we have forward and backward in one formulation, and so it's really difficult to separate them. So what you can.
Why is it not called simulation? Why is this a bisimulation if there is no zag clause?
Well, the zag clause is built in, right? So it's because the formulation here is completely.
Structures are in fact functional structures.
Yes.
Whereas proper graphs are relational structures.
Besides
for relational, and here we have functional. So okay. That's.
Löb, you say it better than I could. Yes, very good. That's the important point. And so, so I'm usually assuming that our graphs are finite, but if we drop that for a moment, we can unravel them, right? So simply take all the directive paths as nodes. And then, of course, you get the two graphs are bisimilar if and only if their unravelings are isomorphic, right? So you can, so you can go, in this case, you can go two ways to find standard representatives of the equivalence classes. You unravel and you get a unique object modulo isomorphism, or you collapse. You take the bisimulation minimal graph, so take the maximal bisimulation. That's an equivalence relation. You can divide it out, and you get a I'm not saying this well. So take the maximal auto bisimulation of a graph. Then it turns out to be an equivalence relation. You can divide that out, and then the collapse will be the bisimulation minimal one, and it will turn out to be unique, right? So whenever two graphs are bisimilar, their bisimulation collapses will be isomorphic. So there's two kinds of salient normal forms, right? And of course, these things are also the corresponding AFA sets. Okay, so now this is, of course, rough, also the kind of thing that Barwis and Etchemendy are doing, but there's one difference. So we have the notion of guard. So what is a guard in a graph? Well, it's a set of nodes such that every cycle contains an element of the guard, right? So yeah, that's the whole thing. And so of course, if we allow infinite graphs, so the notion of guard as I formulated here is designed for finite graphs, but if you allow infinite graphs, it simply is that every infinite path contains an element of G, right? Where the infinite path could start anywhere. And so if we have the guards, we have some kind of useful things. We have guard induction that tells us that if a property is given on the guard, and if it propagates from successors of a node to the node, then we have the properties on all the nodes, right? So that's guard induction. And similarly, you have guard recursion. So if values are given on the guard, and if whenever we have values on the successors, we can form a value on the original node in a systematic way, then we can get values everywhere, right? So that's guard recursion. And important thing is that if the guard itself is preserved under a bisimulation, and if the values that you give on the guard are also similarly preserved, then all the values will be preserved under bisimulation, right? So if your starting position is sufficiently bisimilar, the result of the recursion also will be sufficiently bisimilar. And so these are, of course, the So without these principles, you couldn't really work with these things, right? So this is really important. And of course, if you think about it, so the guard recursion is just a version of bar recursion, and guard induction is just a kind of bar induction. Okay, now, well, a node with label A will be an occurrence of A. We take as labels propositional variables and the connectives. And now finally, I can tell you what the formula is. A formula is simply a graph with this designated set of labels. And we simply demand that the box occurrences form a guard. And so that's it. So note that that the box occurrences that are on a cycle also form a guard. And in fact, it turns out that I'm in the whole development in the paper, I'm using both guard induction and recursion for the two choices of what the guard are, right? So both are extremely useful to use. Okay, so now, of course, so now we have the formulas, and so I've thrown out the inductive way of looking at formulas completely at this point, but of course this is not good for thinking. And so we do need operations on the formulas to form new formulas from old formulas. And so we have the operation of conjunction that par abus de langage I'm writing as using the label as now as for the operation. So how do we form the conjunction of two formulas? Well, simply first take the disjoint union of their nodes, or of the graphs that are the formulas. Step one. Now add a root and label it conjunction, right? So that's conjunction, and similar for the other connectives and the propositional variables. So of course, always you will meet the point where the overloading of notation is a problem, but I think it's, for reading, it's so pleasant that one should keep it and simply have special measures at the moment that it becomes problematic. Now, substitution is, of course, as expected. You simply replace the nodes that are labeled by the variables by the graphs that are supposed to be substituted. Now we have the fixed point, the p fixed point of phi. So that's, I think, a very important operation. It is the result. So given your graph, identify all the nodes that are labeled with p, simply identify them with the root, and let the root keep its label, right? We throw away the label p, and yeah, so it's simply identify all nodes labeled p with the root. That's all. So that's the fixed, taking the fixed points, and so that gives you so now it's important. So that only gives us a formula, this operation, when phi is modulized in p, and so modulized in p means that every pass from the root to p passes through a box occurrence, right? Mm-hmm. So that's really our. So now you see how our the usual notion of modulized turns up, right? So the fixed point operation only gives us a formula if all occurrences of p are modulized, right? So you cannot reach them without going through a box, because otherwise you would form a loop. If not, you would be able to form a loop on which you do not meet a box occurrence, and we decided that those things are not formulas. Mm-hmm. Is that clear? I think this is the kind of really crucial point. Mm-hmm. And now there's also
this is very similar to what Daniel had in his system of proofs forgot Löb logic, where
Yes, yes,
where he had this condition that it should pass through.
precisely.
Necessitation.
Yes,
Mhm.
yeah, yeah. And so this is one thing I forgot to mention at the beginning. Of course, what I'm doing here should be integrated with what Daniel has been doing, but of course, well, I didn't think about that yet, but I think it's kind of so circular formulas ask for circular proofs, but yeah.
Definitely, they look more canonical than the format that you mentioned first, where you have this explicit F operator.
Yeah.
And then you will have all kinds of problems with renaming variables, etc.
Precisely. Yeah, I really got completely crazy because because the renaming variables is kind of a very crucial thing, and so it's really a headache. It's okay. So now there's here. So all these, I think that will be on the next slide, but I can't say it. So all the operations that we saw until now are bisimulation preserving, right? So they are good operations, but I think so. We do need one bad operation, and that's the lightning, lightning strike. So given phi, right? Take a fresh variable p, and now what you do is take the root and split it in two. So one of the two copies of the root keeps all the incoming arrows of the root, and the other copy is left with all the outgoing arrows. Now the copy with the outgoing arrows is still the root and keeps its label. The copy with the incoming arrows is now relabeled P. Right, so that's this is kind of non-deterministic subformula that you form of phi. In fact, well, only of course if the root does have incoming arrows. So it's so if you think of d gamma p phi of p in the standard thing, so then you have the subformula phi of p, right, of the fixed point formula, and in some sense, this phi lightning strike p is in fact this inner formula, as we will see in a moment. So that's the kind of important thing, and so in many inductions we use precisely this notion.
So it's a kind of inverse to d gamma operation.
Yes, it's a kind of inverse to d gamma, right? I will come back to that in a moment. I will show you the equation that is relevant. Yes, but that's precisely it. Well, in fact, if you apply d gamma to this, you get the same back, phi back, but it's not the other way around. If you first do d gamma and then lightning strike, then you don't get then it's not identity. Okay, here is so this is, I think, so my didactic example. So look at a formula with main connective conjunction, right? And so I just made one simple one, but I think you will all be able to see the complete generality of this example. So look at the formula to the right, right? It's a conjunction of something, and then goes to P, it goes to the box, and then it leads back to the root. And now look at the conjunction. So now look at the successor graphs of this formula, right? So that's P, and then it's a formula that starts with a box.
Now we don't see your little hand on your screen.
Oh, all right.
With that,
okay. So what are the successor graphs of conjunction here, right? So it's this single node P, and it is something that starts with a box, and then you have this the whole thing then follows again, right? So one successor graph is this, and the successor graph of for the right hand side is this one, right? It's the whole thing again, right? Because this goes back to the root. And so this is the conjunction of the successor graphs of the root here. And so that looks like this, right? But you see that these graphs are not the same. But now, of course, so here you see also the great importance of bisimulation. Bisimulation kicks in because they are bisimilar, right? So I connect these and I connect this one with that one. I connect this one with that one and that one. I connect this one with that one and that one with that one. And then you can check that that's a bisimulation. So yes, conjunction. So not every graph has modulo isomorphism, the form of a conjunction, but every graph with main connective conjunction is bisimilar to a conjunction, right? So that's the lesson you can see. Lev, is that clear?
Yes.
Yeah. Yeah. So here you see, of course, it really tells us also that phi is bisimilar to phi, p and box phi. And you see immediately also here a nice fixed point equation, right? So
in this context, the bisimulations, they all look like unravelings or something like that, right? So you don't have any more complicated.
No, they're very simple. They're really yeah. So in fact, this formula, yeah, you're quite right. So this is a partial unraveling of this one, right? So yeah, I already explained to this I already explained, so we can go on. Okay, yeah, we already have seen that. So if we have a conjunction, the main connective is a conjunction, and if the generated things are psi and chi, that of the successors, then of course phi is bisimilar to the conjunction. The same thing holds, and in fact you can prove that all formulas can be generated from the atoms by the operations associated with the connectives plus the d gamma operator, right, which you can use to form cycles. And you apply this to modularized formulas, but you can as easily prove that you only need to apply it to boxed formulas. So this is okay. So this is the thing that Lev already saw, right? So that if we take the lightning strike of phi, and then the fixed point, of course, we get back, right? So we simply first take things apart and then we put them together again. So we first break it and then we put it together again. So that's clearly the identity. But the other way, it's not the same, because the point is, of course, phi already could have incoming arrows. The root could have already, of phi could already have incoming arrows, and so the fixed point only adds them. And so if you break them, you break not only the added incoming arrows, but the rest also, right? So then we do not get phi back because we broke more incoming arrows than we do want. So it's important to, yeah. And it's also very important to remember, if you really want to work with this, that this is not bisimulation invariant, or that the lightning strike itself is not bisimulation invariant. So what we also have, and I think this is the effect, the fixed point operation, right? So if we do the lightning strike and then substitute phi for p, then you also get phi back. Right, so that because then you get the only thing that happens here is a kind of unraveling, right? So you yeah, and so this is really, in some sense, you could say also a kind of fixed point equation. And so this one is quite interesting, because if I try to work out this business of fixed point logic in a very general way, and if you do that in the standard syntax, then this is kind of principle that you could, so well, it becomes provable if we have Löb's rule, but it does not. It does not seem to be something that is generally valid, right? So if we first take the fixed point with respect to Q and then to P, so in this setup, it's the same thing that if we first replace Q by P and then take the fixed point for the whole thing, right? So here we first.
So may I interrupt? So I think you haven't yet fully explained to us the workings of substitution here. So this P double dot phi. Yes.
Yeah. Okay. What I said is that.
So maybe it's good to explain the previous bisimulation more carefully, so to say. So
this one.
Mm-hmm. Yeah. Yes. Mm-hmm.
Okay. So the idea is this, right? So now first we have phi.
So what is P double dot phi? Well, that's the question.
Sorry?
So
okay. Yeah, so the substitution, so what you do is simply you go to the node, all the occurrences of P.
Mm-hmm.
And so phi is a graph, and you simply replace the occurrence of P by the root of phi, right? So substitution in the graph theoretic context is simply replacing all the nodes labeled by the appropriate variable by the substituee, right?
So do we copy this graph of phi many times, or do we have a single copy which we somehow connect to all the points?
It doesn't matter. Well, yeah. The way I set it up, you get a lot of different copies, but it's immaterial because modulo bisimulation, your way. So I could first identify all nodes labeled P modulo bisimulation because they're end nodes. So I can always arrange that.
These are the end nodes. Okay.
I can always arrange that every variable has precisely one occurrence modulo bisimulation, right? So, so yes. So
indeed.
Yeah, no, that's the miracle of thinking modulo bisimulation, right? So this kind of details should be
irrelevant. Yeah, important thing I didn't I forgot that P is a variable, therefore it's at the top node, so to say, in this this structure, and then you can sort of grow one copy or several copies of phi in these leaves. So
yes, precisely. Yes. Yeah. Okay, but so the interesting thing of the last one here is so that you somehow the circular syntax has a mind of its own, and it adds a principle that, at least when I was thinking about the standard syntax, was not obvious to me. Okay, now we are finally there. Okay, I'm doing very well with my time. Now we can finally give our notion, our logic, and it's very simple. So we have the axioms and rules of K.
Sorry, Albert, I didn't see other Boolean connectives. Maybe I missed them. So was there disjunction and negation as well, or?
Yes. This is the usual connectives: conjunction, negation, the box, implication. Doesn't really matter as long as it's the usual bunch. So conjunction is just my standard example, but yeah. It's and I have also falsity and truths, which are also end nodes, right? So they don't have out, so their arity is 0, so they don't have outgoing. So you only get the empty sequence of successors. Yeah, is that clear? Okay, so we have.
You also duplicate, make 2 copies or however many copies of the graph you need depending on the arity of the connective, or what? just like we do
Yes.
conjunction.
Yeah, but yeah. Yes, yes. So yeah, right. So box phi, that's the graph which has first a node labeled box, and then and the successor graph is phi, right? Tadeusz, are you there?
So this sounds then like more like a syntax tree than I expected.
Yeah.
Yeah, it's essentially a cyclic syntax tree. So
yes, precisely. Yes. Yeah, and the point is that you can always
yeah.
So the point is you can always unravel it a bit to make the first part look like a tree, right? So we can always postpone the cyclicity arbitrarily far modulo bisimulation, right? So that's partial unravelings. And so we have K, we have Löb's rule, which now suddenly gets byte. And we have one axiom that really expresses that bisimilarity is our real notion of identity of formulas, right? So so if we have two formulas that are bisimilar, they are of course also equivalent. But so the important thing is that this axiom 3 is not really an axiom, right? It's really it's really an artifact of the fact that it's technically convenient to have the and also I think for our minds it's good to have the copies modulo isomorphism before our.
Let's call it a structural rule or something like this.
Yeah, right, something like that. Yes, precisely. It's yeah, it has a special status, and yeah, and so I claim that in some sense this is cyclic K, but of course you also have it without Löb's rule, but then suddenly you can do far less.
Mm-hmm.
Okay, now now the important thing is that we can start to work in this logic, and yeah, a very important tool is what I call the Gullet modality. So
okay, Albert. So before you proceed, so let's decide. So what part of your talk will be today, and what we will postpone till next time.
Okay, very good.
I think 8 o'clock for finishing our the talk will be the right.
That's
right.
6 o'clock here, right?
That's probably 6 o'clock there. Yeah.
Okay, then we stop. Why not? So I have introduced the logic. So I'm really halfway now. So
maybe some examples of some derivations in this system would be nice to have as an illustration or something. So if maybe I would like to see some. Maybe the next slide will be the where you.
Well, I'm not really giving.
You are entering the proof of the uniqueness of fixed points, right? So that's what you are about to.
Yeah.
Do now. Okay. Mm-hmm.
Yeah. Well, so the proofs can look rather. I think the proofs in my system look rather conventional, right? We can work with them very much as in a usual system because we have these operations, right? And so okay, maybe yeah. So look at the Gullet modality, right? So that's really the fixed point of box phi and p, where p is fresh. And so the whole thing is that so even if the box is not transitive, that doesn't have the transitivity axiom, we can out of we can out of nothing conjure up a transitive thing, right? Because the namely we say it's so this is really box phi and right. So it's really the fixed point of the conjunction of box of phi and then the same, right? And so what you get, of course, is this. Yeah, right. So so maybe that's a good. So the only thing is that now I cannot use the blackboard, and I'm
you can actually write on your slides with your mouse if you want the comment. So there is this possibility of comment your slides.
And where is it?
Let me see.
Not to mention that if you are an Apple person and if you have your iPad and your magic pencil, then your possibilities increase. But
maybe
thank you for this very helpful remark.
Okay, I think probably I switched this possibility off in fear of possible Zoom bombing.
Okay.
But next time we will switch it on. So
okay, well, maybe I can try to do it in words, right? So that will. Okay, so now let's try to prove the transitivity axiom for box-Grollet, right? So now assume that we have box of the transitivity axiom. So box-Grollet implies box-Grollet, right? And then now assume box-Grollet phi. Right. So that gives us, using this definitory axiom, gives us box phi and box-Grollet phi, right? So now, but since that gives this by itself gives us box-Grollet phi, but also we have under the box assumed that box-Grollet implies box-Grollet. So we have what we get is box-Grollet phi and box-Grollet phi, right? And now we use this axiom in the other direction, and we'll see that what is there is simply box-Grollet phi, right? And so from the assumption of the provability of box-Grollet implies box-Grollet, we have derived box-Grollet implies box-Grollet, and then you apply the Löb's rule and you get the transitivity axiom for the Grollet modality. Yeah?
Yes.
And similarly, because you really now need to prove, for example, that it satisfies the second Löb condition. And you do the you do the same kind of trick, right? So you assume box of box-Grollet phi and box-Grollet phi implies psi implies box-Grollet psi, and then you run through the whole kind of reasoning again, and you find that the condition without the box, and you apply the Löb's rule, and you're done. And similarly, also for necessitation, right? So we verify Löb's logic, full ordinary Löb's logic for the Grollet modality. And okay, so now maybe I will start here again at this point in the next lecture. So, but maybe just as the real achievement, the real thing that you have to do, the central thing is the substitution of equivalence. So that's so the proof of that is not difficult in some sense, but I wrestled with it for a long time to get all the subtleties right? Because here you need this kind of guard induction, etc. So in fact, I found what all the necessary proof methods are, in fact, by thinking about this proof. So it's not difficult. So if it's written up, it's also quite short. But it's the substitution of equivalence is the kind of center. And if you have that, then everything follows in some sense easily.
Mhm.
So
Okay,
shall we do
anyway,
questions?
let's start next time with this with this proof of
Yeah.
substitution
And if
principle.
you wish, I can write out I can write out a specific example of a proof, etc. So maybe we could also convene with the two of us, and you can teach me how to write on the slides.
On the whiteboard. Okay, that all possibilities are good. So I can do so. But do you have something with which to write except your mouse, or you just have your mouse?
Just
okay.
I'm a kind of computer challenged person.
You don't have
But
to teach in Zoom. That's the only, that's the blessing of retirement, so to say.
Blessing of retirement that you can admit all your weaknesses.
Okay.
But you have an iPad, right? So maybe you can write with your finger on an iPad at least.
Yes,
If
this
you
was
have an
exactly my
iPad,
suggestion
if
too.
you-
Yeah.
If you have an iPad, that works well.
Oh, okay.
And maybe someone with iPad should teach you, because I don't have iPad.
Ask your kids. That's the best way to go.
Well, I have an iPad but a newer model. So if you have a newer model, you could buy Apple Pencil, and then you could write like with stylus, like with a proper tablet. But
I'm not going to do all that.
Prime point.
Anyway.
Fat point with your finger.
Anyway, we decide what to do best until next time. Okay. If anyone has questions to Albert, then please ask.
maybe one comment. So this, I don't know if it's intended to happen later in the presentation by this modality in its own right. So if you want to have another language without variables, you can simply add the modality only to so the transitive closure, which is something also similar to what happened sometimes in the past, just that now we have this K rule for the basic box modality. And putting aside the questions of equivalence or conciseness, at least the completeness proof for the, even for the fixed point calculus, can go via completeness proof for this much simpler language. So this is yet another way of doing away with this whole binding circus.
Yeah.
So that's
okay. I will say something about that, Tadeusz, in the next time, right? So that it's because this is closely connected with the things of systems of equations. So yes, you can in some sense reduce this calculus to the thing where you have the box and the box Grölet, but now as primitive things. So you don't have any, and with standard syntax. But then, of course, the effect of this is that you really, so it's a little bit like in the Solovay style axiomatization of Solovay's logic. You really need a kind of big conjunction of box Grölet dot, which means box Grölet true phi and box Grölet phi. You have a big conjunction of these things of fixed points, and then they imply something, right? So, and that's one possible reduction of this system. So there are in fact several ones. So you can translate it into the standard syntax with the gamma operator. You can translate it in this system with the fixed points, the constants for fixed points, and you can do this. You can do it here in the Grölet system, but then you use a big antecedent with a number of fixed point equations, and in fact, But if, in fact, Thaddeus, to find what the fixed point equations are, you need guard recursion, right? So you can read out the appropriate fixed point equations very easily from the graph using guard recursion. And so, in fact, conceptually, the circular setup really helps you to understand what's going on in the Gullet, the pure Gullet setup. Yeah, but I will, yeah. So I'm at the end of the talk. I have something about the modal completeness. So so yeah. So one road is to reduce the modal completeness to the well-known. That's what Thaddeus is quoting, to the known modal completeness of this.
Not so well known. Okay, so we had to.
Are we already completely sure of the proof?
Yes, we are. We are. Okay, we have to agree on this before your next presentation, but we are.
But the other way to have the complete. So I will also say something about this later, because this calculus is also synonymous with the mu calculus plus the minimal Henkin fixed point as axiom, right? And so we also have already the completeness theorem for this, the mu calculus. And so you can also use the completeness theorem for the mu calculus to give a Kripke completeness for this one. So there's really two roads, I think. So where of course in some sense the road via the box Gullet is the simplest one, because the mu calculus is a kind of big difficult thing.
One more question about this variable freeze or graphical syntax. Did you also look at what people in more categorical setting are doing, like this whole business of traced categories, for example, because they are often also working with this pictorial kind of formalism where you also represent fixed points with kind of loops. So is there a meaningful relationship here? Or?
I don't know, but I'm almost sure that there should be.
Okay.
Right? So, how many ways of thinking about fixed points could there be? I'm just saying that this is a
modulo bisimulation, right? So there is maybe not isomorphic ways of thinking about fixed points.
I'm just saying that this fixed point, this way of doing it is kind of a really good one, and yeah, it has this kind of pictorial advantages. So yeah, something that I wanted, because I suspect very strongly. So we're, in some sense, we are just looking at the analog of the rational numbers, right? So you can also drop the finiteness constraint on the graphs, and if the thing is sufficiently if the representation of the graph is sufficiently effective. So I tend to believe that even the arithmetical interpretations can be done, and so so that would be a kind of also interesting for piano, and as an extension of the language of ordinary provability logic, that you have the kind of the reals, as it were, of the ordinary formulas, which are the rational numbers. And so what happens then? That would be a kind of exciting perspective that you could get from this.
Speaking of which, I realize now that even closer match would be what they do in this theory of lambda calculus or lambda trees in terms of rational trees. They also do it, again, they also do it in categorical setting with monads, but this is another connection to
yeah. No, absolutely. So I'm fully sure. So I'm not, of course, I took the idea of treating the circular syntax simply literally from Barwise and Etchemendy. So the whole thing that you have to add to get our good old provability logic from it is to add the idea of the bar or the guard, right? So it's Barwise and Etchemendy wanted really to study the paradoxes and created the kind of circular environment to study those, but we want to block the paradoxes, and hence that you add this idea of guardedness.
Speaking of this idea of Barwise and Jongh-Sambin-Bernardi, Alexandru Baldac pushed it quite far in one of his very early work in first IML, I think, where he built a model for anti-well-funded ZF precisely out of equivalence classes in wait, what was it?
That cannot be Alexandru. That sounds like a very old result, which is in Peter Axel's book.
Yeah, so he was definitely building on Peter Axel's book, but wait. So I need to double check. We can get back to it.
Well, we have next time. So
yes.
I think that thanks to Lev, we have a kind of very generous time to think about these things.
Mm-hmm.
But there's yeah.
Okay, anyone else has any remarks or comments? Maybe Daniel?
I do have a question. Okay, so Albert, so do I understand correctly with regard to the first part of your talk, that basically if you apply this to, say, Fermanian probability predicates over PA, that essentially gives you, so the closure under Löb rule gives you this restriction of what kind of probability logics of Fermanian predicates we could have over P other arithmetic or its extensions.
Sorry, so I heard what you said. What is the question?
Well, the question was I understand correctly that basically the first half of your talk, so it gives some limitation of what could be probability logics of the Fermanian probability predicates.
Yes. And so that also works over, yeah, I think that's, so Kurahashi has all this work about the sigma 2 predicates. So sigma 2 axiomatizations of piano over piano, but I have not, so, and of course you can do a lot of things, but I have not thought about, so the precise, so you can get precisely K, that's one of his most amazing results. But yeah, it would be extremely interesting to see what happens if there we add the fixed points, right? So that could very well fall under this work, but I haven't checked whether his interpretations are uniform. So that's the main point. So there's still some real work to do to check what happens with examples in the literature. So I don't know, right? So my favorite really is elementary arithmetic without sigma 1 collection that really behaves very, where you can get all kinds of crazy behavior with respect to sigma 1 axiomatizations, which is a kind of fun. So that's what I've thought about, but undoubtedly you can also do all kinds of things with sigma 2 axiomatizations of piano. It's yeah, at some point someone, maybe I, but maybe someone else, should do the homework and look at what Kurahashi's examples do if you add the fixed point calculus. It's
sorry.
Yes. It seems for me that this extended logic K with the Löb's rule can be also presented in the form of K without Löb's rule, but with cyclic proofs and Hilbert-style form or a sequence-style form. So,
yeah, that I would hope that's true. Yes.
Yeah, it seems rather
plausible.
Plausible, yes.
Yeah.
And as I recall, we had also a short correspondence with after your St. Petersburg's talk on non-well-founded formulas, or regular non-well-founded formulas and GL, where we also considered syntactic proof of this fixed point theorem for GL with these regular formulas. So, indeed, there is a connection. There is
the regular fixed point theorem becomes a matter of course in this context, right? So the usual the Jongh-Sambin theorem of the explicit fixed point. So the whole point is that you can read off using this guard recursion. You can read off immediately the form where you only consider fixed points for boxed formulas, not just modalized, but with main connective box. And then, so that's the syntactic part. And then the content part is, of course, that for boxed formulas, that box phi true is the fixed point of box phi p, right? And so that's the content part, and that uses second Löb condition, right? Box implies box box. So that's yeah. So indeed. So in fact, this was one of my inspirations to think about this anyway, to have kind of more systematic understanding of the usual fixed point calculation in provability logic. Yeah. So, but I don't know. Am I answering your question, or did you want to?
That was a remark. That was a remark.
Okay.
And maybe a question. I wonder what directions do you think there are in studying such type of systems of cyclic formulas or cyclic proofs? What is your intuition? What are questions which are
I think I think there's some really exciting questions. So the first one, so I will explain a little bit about, of course, arithmetical interpretations. So, and it seems to me, even if I have not really checked it in detail, it seems to me that this also would work. So, well, I haven't defined all this, right? But suppose that we allow really infinite graphs. So so one that for which the bisimulation collapse also is infinite, and that could probably even be on finitely many propositional variables, if I'm right. And I suppose that we can define what it would be for that thing to be recursive or something like it, right? Or decidable in some sense. So it seems to me that you can define arithmetical interpretations for such generalized formulas just as I do it here, right? So and prove also the uniqueness. So that's one, I think, interesting thing. So these are the rational numbers. So what are the reals, or at least the recursive reals? So and does it give us anything interesting? Because of course that's not clear to me at all whether, so can we prove Solovey's theorem for this kind of generalized interpretation? So simply for PA, that's all open. So the second thing is, so I'm going to, so it seems that if we want to do the mu calculus on the circular syntax, it seems that, so then the kind of representation that Löb wanted is in fact a little bit better. So if you have arrows that are labeled plus and arrows that are labeled minus, and so I think for the mu calculus demand should be that if you run in a cycle, the number of minuses on the cycle should be even, right? So that should be the mu calculus formula in this syntax. But I have no idea how one would precisely treat this, right? Because you don't have a guard, but something else. How does that work? What kind of recursion and induction do you have there? I have no idea. But since my calculus here, or in fact, I should also say Thaddeus and my calculus, because we had it first for the straight syntax. So if you look at this calculus or this logic, that's really modulo synonymy, a subcalculus of the mu calculus, right? So it's simply adding the minimal Henkin sentence. And so there should be an understandable connection. But yeah, so we only understand this connection via the straight syntax. So it would be beautiful to understand it immediately by thinking of this also on a circular syntax and to do that. So that's also kind of completely terra incognita, but I think that would be a kind of exciting direction. And of course, what we have been talking about, right? Integrating all this with the circular proofs so that you get a kind of, because I think there's a felt harmony between this kind of idea and the circular proof kind of idea. And so we even would want to get rid of Löb's rule to, yeah, well.
I would like to add some remark to the first question concerning fair, non-well-founded formulas with this guard condition on infinite branches. As I understand, if we consider this question algebraically, as I understand, Avogadro algebra admits addition this kind of solution of infinite fixed point of infinite set of equations, if and only if this Avogadro algebra is box founded.
Yes.
This extension is unique, as I understand. It seems to be so. And in the case of piano arithmetic, it's probability algebra. I guess it's some notion of probably recursive box foundness or something like that could be introduced. Maybe Fyodor could explain it better, but I remember in his paper with James Walsh, he recalled this Soloway's theorem, as I remember, that there is no provably recursive decreasing sequence of sentences with respect to this consistency order. And it means that this probability algebra is in some sense box founded, but with respect with this probably recursive chains.
Yeah.
So surely there are some connections, but I guess we need to find some language to relate, to speak about these matters.
Yeah.
Beautifully.
Yeah.
Yeah, so with regard to so this infinite distinct chains in Avogadro algebra of piano arithmetic, as far as I remember, so the chains that do not exist are this recursive chain such that the fact that the descending is provable, something like that.
Precisely.
Yeah.
So it's probably a recursive version of this box foundness condition on Avogadro algebras.
Yeah, but maybe because the but not before the next week, I'll try to work out how my embedding of the, well, maybe a kind of rough sketch of how this embedding of the infinite case would work, right? It really uses, of course, the fixed point or the recursion theorem with free parameters in piano arithmetic, right? So it's really, of course, for the finite thing, we can all do everything with concrete fixed points, but
Mhm.
the general case, we have to do this uniformly, right? So that there's a variable there. And so maybe this has to do with, that should be connected with the kind of constraint on your algebra. But maybe it's wiser to first try to to give the straightforward proof and then try to connect it with the algebras. But yeah.
Yeah, I mean, the topic pulls too many strings in our souls.
Yes. No, sure. Yes, it's true. It's true.
Endless bottomless Russian souls. Right? You just
No,
dive into it and you never get out.
there is in some sense too much to do. Yeah.
Okay. But
Just
there will be
let-
next round of questions next week, of course. So,
just let me add clarification that because I'm angry at myself for messing this up. So the I posted it in the chat. Baltak's papers in question was about using infinitary modal logic as a foundational language for Axel's ZFA. I posted a link. So especially now that infinite stuff started to come up, but I don't know. Let's not get there. Let's not go anywhere. Let's just go for it.
It's an interesting question. So because my infinitary logic is lengthwise, the depths of the formula, right? So the usual ones have big conjunctions and big disjunctions make the formula very fat, but I make the formula very long, so to speak. So it's so I'm really curious whether there are analogs, analogous infinitary logics of the long thin kind and not the fat kind, right? Because the definitions really constrain. It really should be it cannot be fatter, it can only be very long. Okay, let's talk next week.
okay, thank you very much.
Thank you.
Bye-bye.
It was very nice.